Hi, this is Kishore Kumar. In today's video, I am going to explain a very dangerous fault in three-phase, four-wire systems. This is the setup which I will explain now. This video will be very useful for electrical students, technicians, and professionals also. Before going into the demo, we will go through some notes. Here is the note. The title is Floating Neutral Fault in Three-Phase Four-Wire System. The voltage is 415 volts between lines and 240 between phases and neutral. So we will go into note number 1. If the load in all the three single phases are same or balanced, then neutral is not required. Point 2. If the load in all the three single phases are not same or unbalanced, then neutral is must. In this condition, if the neutral is cut, open, disconnected or loose, then the voltage in the three phases will differ from low to high voltage according to the imbalance. In this case, it can vary from 0 to 415 volts. So due to low and high voltage, all appliances connected to those circuits will get damaged, especially electronic appliances, as these are very sensitive to voltage ups and downs. Neutral acts as balancer. RCCB will not trip for this fault. So we will go into the demo. First, as I told you, I will explain the setup. Actually, this is the board, demo board. Here I have a multimeter. And the input supply. This is three-phase supply, R, Y, B. You can see R, Y and B. They are connected to breakers, which is in off position. This is the inlet for the demo board, RYB, and from here I have taken the neutral. So here are the three phases, and neutral I have taken from here, which is a separate socket. I will show you now. So this is the neutral pin. This is phase which is not required. I have connected the neutral to the common star point via this on-off switch. This switch is for neutral. comes into the switch and goes out and is connected to the star point, which is common for all the three phases. So if I can disconnect and connect the neutral, this is connected and this is disconnect, off and on. Now it is off, now it is on. The purpose you will understand shortly. So to all the three phases, I have added bulbs as loads. Per phase I have added 2 bulbs. You can see here, this is red phase, 2 bulbs. This is yellow phase, 2 bulbs. And this is B phase with 2 bulbs. You can find the neutrals for each phase. Here the black wire is the neutral. Here you can see. For blue phase, this black is for the yellow phase and this one is for the red phase. And you can see all the 3 neutrals I have linked here. 1, 2 and 3. So simply put, I have connected 2 bulbs in series for each phase, R, Y and B. You can notice the watts. They are all same. That is balance, 10 watt, 10, 10, 10, 10, 10. So you can assume the load connected to each phase, each of the 3 phase is same or balanced. You may wonder why I have connected 2 bulbs in series. It is for withstanding the high voltage created when the neutral is disconnected. So only I have used 2 bulbs in serial for each phase. Now we will go into the demo. Please watch the readings carefully while doing the demo. So we will check the nodes one by one. The initial system is 3-phase 4-wire system. So 3-phase, phase R, phase Y, phase B and the neutral. So this is okay. And the voltage is 415 between lines and 240 between phases and neutral. We will check it. Now I am taking the multimeter, set in voltage, AC voltage. I will show you. I will change to AC. AC and light, backlight. and I will switch on carefully. So now I will check between the voltage between the lines, line to line, between R and Y. You have 418 volts. Between Y and B, you have 413 volts. Now between R and B, you have 417 volts. RY, YB, then RB. Okay, now? So I will switch off. Now we have checked the voltage between lines. Now between each phase and neutral we will check the voltage. It may not be 240, it may vary by 10 volts like that. Now what I have to do is, I have to remove this probe. For convenience, I have to remove this probe. And I am attaching a probe with banana at one end and crocodile clip at the other end, just for convenience. So you have to be careful. Check whether it is in off condition, and now I am clamping it to the common link, neutral link or start point. Now I will switch on the three phases. We will check each phase and neutral. Already neutral I have connected. Please watch the reading. So 213, 240, 242, 242. Again I will show you. 236, 242, 242. So we have checked this parameter also. I will put a tick mark. Now we will go to note number 1. If the load in all the three single phases are same or balanced, then neutral is not required. Oh, this may be puzzling or funny to you, but now we are going to see that. As I already told you, in all the phases the load is same, that is 20 watts, 20 watts, 20 watts. And here you are having the neutral in on. Okay. Now I will just switch off the neutral. The neutral is switch off. That means the neutral has been disconnected. Even here I will show you. See, it is disconnected. No neutral. That's no problem. There's no need for return path for carrying the return current. Please note carefully. You can see all the bulbs are lit. So in this condition, we will check the voltage between each phase and neutral. That is between each phase and neutral. The voltage is 230, we will assume it as 234. That is between R and neutral, between Y and neutral. That's not much difference. It is within the limits. So now we know the voltage is more or less equal in all the three phases. Now what I will do is I will connect the neutral. There's no need to remove this, but for clarity I have removed this. This switch itself will do this work of connecting and disconnecting. So this point we have checked. That is, if the load in all the three single phases are same or balanced, then neutral is not required. Now we will go to the second note. If the load in all the three phases are not same or unbalanced, then neutral is must. In this condition, if the neutral is cut, open, disconnected or loose, then the voltage in the three phases will differ from low to high voltage according to the imbalance. In this case, it can vary from 0 to 415 volt. So due to low and high voltage, all appliances connected to the circuit will get damaged, especially electronic appliances, as these are sensitive to voltage ups and downs. Now we have to check 2 points. One is with the different loads, that is unbalanced. We will create an unbalance by changing the wattage, different wattage bulbs. I hope you understood. Suppose if there is a the load is equal, then neutral is not required. If the load is not same, that is, if the load is unbalanced in each phase, then the neutral is must, otherwise the voltage will float. I want to go to the third point also. Neutral acts as a balancer. So this we have to prove. We will prove that, this point. So what we will do, we will switch off. And we will let it be in the off position. I am going to change the load by changing the wattage of the bulbs. This is 7 watt, as you can see. Watt, and here also I have to change. I am creating an unbalanced load for which balancing neutral is must. This is 9 watt. So now the loads in each phase are different. This is 10 plus 7, 17 in a red phase. In yellow phase it is 10 plus 9 is 19. And in blue phase it is 10 plus 10, 20. So please understand, this is 17, this is 19, and this is 20. The loads are not in balance. Now we are going to switch on the neutral first, then the phases. So now what we are going to do is, we are going to check the voltage between the, I will do one thing, I will cover these bulbs. So there won't be distortion while taking the video. So neutral is on and all the phases are on. Now the entire circuit is, whether it is balanced or not, we don't know. For that we are going to check the voltage. Just a minute. On AC backlight. For that we will check the voltage between individual voltages between each phase and neutral. Please note the readings. First between R and neutral. It is 240. Between Y and neutral, 244. Between blue and B and neutral 232. More or less, these are all same within the limits. So these slight variations we can ignore. Now what I will do, we have to prove the second point. First, with the voltage between phase and neutral, with the neutral on. Now we have to disconnect the neutral and see what is happening to the voltage. Now I am disconnecting the I have disconnected the neutral. For clarity, I will remove this also. Now there's no neutral. Now we will check the voltages between each phase and neutral. Please watch the screen carefully. Between R and neutral, 330 volts. Suppose if I am using one bulb, that would have burned away. This bulb is on. So see here, 330 volts. 330. Now between Y and neutral, 225. Now between blue and B and neutral, 200, 203. See, note the difference. This is the lowest. And this is the highest, 330. So low voltage, high voltage and normal voltage. It depends upon the load and the voltage between the phases. It is looping between the phases because there's no return path. It is completely disconnected. The service neutral has been disconnected. So this is the important movement. So suppose if I connect a laptop charger and it is getting charged and suddenly the neutral gets disconnected. See. Now neutral is connected and the voltage is 241. And suppose if I off, just a minute. Watch carefully. Wait. So I will catch like this. Okay, no problem. I will catch it with my leg. So I am disconnecting the neutral. Just watch the display. On 240, disconnect 330. So naturally, the extra voltage will definitely destroy the charger as well as the laptop. The electronic appliances with board are very sensitive. They cannot withstand very high voltages. If the voltage is low, then it won't work properly. All appliances. So you have to be careful that the neutral is intact. The integrity of the neutral should be very high. So we have seen if the load in all the three single phases are not same or unbalanced, then neutral is must. That we have checked now. Differ from to high voltage according to the imbalance. In this case, it will vary from 0 to 415, we have seen. So due to low voltage and high voltage, all appliances get damaged, especially electronic appliances, as they are sensitive to voltage ups and downs. Then the third point, neutral acts as a balancer, we have seen. The fourth point, RCCB will not trip for this fault. Now we are conducting this experiment through an RCC protected supply. It has not tripped. So if any person or YouTuber tells that RCCB will safeguard from neutral, floating neutral fault, it is a lie. They are lying. Don't believe them. So we have seen this also. Actually, this video is a very long video, so I am feeling sorry. And you cannot find this 3-phase 4-wire floating neutral problem anywhere in YouTube. I have not seen. So this is a very, very important fault, a dangerous fault. And I hope I have explained to you and you would have understand this about this fault. If you have any doubts, please comment in the comment box. And also you don't try without guidance by yourself. It is all open and moreover it is 415 volts it will be very dangerous. As I already told you, the RCCB will not trip for this fault. So thank you for watching this video. Bye.